So I chose question 42 for my demonstration, and because it's a rather lengthy question, that's why I opened the actual yellow book, and I'll let you read the question first. So question 42, I will introduce three unknowns, x, y, and z. That will be the amount of land I will cut for. So that's the amount of hectares, number of hectares. I will grow my wheat, x for the wheat, y for oats, and z for barley. That's the model. That's the variables, in fact. If I want to solve my system exactly, remember, let me just bring the table back on. Here's the table. So x goes for wheat, oats, y goes for oats, z for barley. Now I can, using these variables, I can make some equations. For instance, if I grow on x hectares wheat, I will need 6 times x amount of labor, 150 times x amount of fertilizer, 70 times x amount of water. And if I sum up all of the labor requirement in terms of XYZ, all of the fertilizer requirements in terms of XYZ, water requirement in terms of XYZ, they will need to be as my numbers, like here, as my limitations. So the system in part A, they refer to this system. I did all of that, and I come up with the 4 equations. First one, obviously, that's the amount of land I have. Altogether, I have 12 hectares. This is the equation so this one is the land use equation. This one is the labor equation. This is the fertilizer equation. All of the numbers are coming from that table. It's a fertilizer identity. And the final one was the irrigation water. Is the irrigation water. So when they say set up a linear system for the given model, they refer to these equations, to the equation like this. Of course, if we can solve such a system, that will be very optimal usage of my resources, including land, labor, fertilizers, and water. And now we know how to. We don't need. I mean, I'm not going to solve the system right now, but we can. When we have a mechanism how to decide whether the system actually have a solution, we can apply this mechanism. The system is rather huge, so I'm not going to do it manually, and I don't expect you to do it manually. So, but I already pre-computed everything. So if I extract my augmented matrix for the system, here it is. So remember, if I do that, that's my matrix. Here's the first row. These are the coefficients of my first equation. Here's the second row. Coefficients of the second equation. Third row. And the last one. Here's my augmented matrix. I'm going to take this matrix to the row echelon form. I don't expect it, like I didn't do it manually. I didn't do it by Maple either, but you can probably do it if you want. If you will be double checking my workings, you can do it with Maple if you want. In fact, there is a little problem with this. I'll explain it in a second. I have already the row echelon form of this matrix pre-computed on this slide. Here it is. So if I take this to the row echelon form, the row echelon form, it's not going to be looking nice because the numbers are not so nice. So first row, second row, so far so good. No fractions. Third row, and the last one. Here's a row echelon form I came up with while doing the Gaussian elimination on this matrix. Like I said, you can double check this. In fact, double checking row echelon form is a bit tricky because if you just type this matrix into Maple and ask Maple to do row echelon form, you will probably come up with a different result. Because the final version of your row echelon form depends heavily on the choice of the operations, and this choice is not unique most of the time. So if you want to check my particular workings, actually I put here the actual operations I performed. And I did it not with Maple, I did it with the other way, with some other means. So first I did this operation, I put this on a slide. If you challenge my numbers, you can check this following this. Otherwise you can use Maple, but like I said, with Maple most likely you will come up with a different matrix. So I did this set of operations. That's the sequence of elementary row operations which I apply to this matrix in order to come up with my row echelon form. Now, on the principal side, that was the computational side of the business. On the principal side, when you look at this row echelon form, you see immediately a problem for the farmer, isn't it? What's the problem for the farmer? We cannot solve this system exactly because we have a pivot here, rather nasty pivot, but still which ruins the whole thing for the farmer from the exact point of view. We cannot exactly allocate the land so that all of the resources used up to the limit. Now, what's the question? So that answers in fact part B of the question 42. So the answer to that, we cannot solve the system exactly. Now, in part C, they say this. Well, in principle, farmer may just accept some slack in the usage of the resources. So in fact, he doesn't need to solve this system sharply. What he does need, he needs to solve inequalities instead. Meaning that rather than putting the equal signs here, from the farmer's point of view, he's not a mathematician, he doesn't care about the exact solution. He can just, from his point of view, he will be happy if we replace the equal sign with a lesser equal sign. Here, in all four equations, he will be quite happy, or she will be quite happy to accept inequalities here. As long as we're not overstretching our resources, we're happy with that. And yet, under this inequalities, he will be very much interested in the optimal use of the resources. Now, the part C actually suggests what the industry normally does in this case. Because in industry, when they look at the optimal allocation of resources, they come up with the linear systems. Most of the time, these systems are not solvable exactly. So, and part C gives the recipe how to handle this problem. It says, let's just introduce what they call the slack variables. Let's just assume that we have the inequalities here. Then this extra space between the left-hand side and the right-hand side, we can just give a name to this extra value, any name, and we will call this new slack variable. So I'm going to change my system now. It will be still system of linear equations, but this time with a new slack variable. Look at this. First equation will be like this. You see, I introduce a new variable to account for this inequality part. Second one will have its own slack variable, which I called V this time. Third one will have its own slack variable, and that is W. And the last one, I think I chose a name S for that. This inequality side, in terms of these new variables, it can be encoded like this. I require that the slack variables, they are non-zero. You see what happened? At the expense of these new variables, we converted back from the inequality to the equality setting. We're no longer looking at the inequalities anymore. We're still looking at the equalities, but now we have more variables. Yeah, we have more variables, but we know how to deal with this. We can now extract the augmented matrix of this new system and see if we can solve it subject to the extra requirement that the values we come up for the U, V, W, and S, they are non-zero values. If we can come up with such solution, it will be very good solution for the farmer. It will give him the allocation of the resource without going beyond the limits he has or she has. Let's just do that. In fact, if you think about that, I mean, like if I extract the augmented matrix from this new system, here it is. It's a long matrix. I don't expect you to copy that. I will upload the slides, but if you want to copy that, go ahead. Here it is. Here's my new augmented matrix for the new system with the slack variables. Again, if I would like to answer the question whether my system is solvable, this time it probably will be solved. There's too much slack in the system. It will be solvable. I need to take this to the row echelon form again. On the positive side, you can realize that these operations I did with my original matrix, they will work here again, because the first part of my matrix here, it's my original matrix. So if I just use my the same set of the row operations, and those of you who will continue on the computational side of the business, I mean, obviously in the industry when they do that, and they do this very often, I'll comment on that in a second. When they perform these row operations, they sort of build a special abstraction for that, and the computers normally do that. From the optimization point of view, you don't have to do all of the effort you did first time when you did your row echelon form. Knowing the operations beforehand make it even easier to find the row echelon form. Anyway, here it is. We'll just wait a little bit. It's a rather lengthy one. Here it is, quite expectably, the right-hand side of my row echelon form as before. I use the same sort of set of the row operations, so this column is identical to this column. This part of the matrix is identical, well, not first three rows of my matrix, I'm sorry. First three, columns of my matrix, identical to my original first three columns here. These ones, this is a result of my new slack which I introduced. This is obviously a solvable system, right? All pivots on the right-hand side, that's one pivot, that's another pivot, third pivot, fourth new pivot on the left-hand side this time. We know this system is solved. We know this system has multiple solutions. Now, let's just look at the system from the point of view of the farmer. We have to make sure that the solutions I come up with, U, V, W, and S, they are non-negative, right? If you remember how, because we have three non-leading columns here, these columns, that's the columns which correspond. So if I bring up the variables, so here's my slack variables, U, V, W, and S. Slack variables corresponding to my last four columns on the left-hand side. If you remember how we saw the system like this, which has non-leading columns, remember these three variables, we can set these variables to any values we wish. We parameterize them. And then the remaining part of the variable set can be back substituted in terms of these three, V, W, and S. I'm not going to do that. I will back substitute only for one, for U. It's too much to write if I back substitute for everything. I will back substitute only for U variable. If I do that, that's only the last row. Here's a back substitution. Oh, I just realized I made a typo in my back substitution. I wonder if you will find that. That's my back substitution. No, it's a very clear typo, right? Because I typed U on the left-hand side and on the right-hand side. Instead, I should have done it like this. How do I fix that? This one should go, obviously. This should go, and my U on the left-hand side should carry an extra coefficient negative 18 on 5. That's the proper back substitution. Well, it's not the exact value for U. I can solve for this value. Let's just solve for this value for U. Can I solve for it? I can solve for it. Solve for U. Let's just see if I have a nice expression for that. Yeah, that's the solution for U. Now remember, the objective of my farmer, allocate U, V, W, and S so that all of them non-negative. If this task was looking really insurmountable at the beginning, right now it looks very, very easy task, isn't it? Like, for instance, if I set S0, V0, W0, the value for U, well, it will be negative. It's not a good choice. Or actually, it's a good question right now. Because of the typo, originally when I was looking at the slide, I was thinking of one way of choosing non-negative values for U, V, W, and S, and that looked all right to me. But because now I realize there's a typo, I have to make another choice. And let's just spend 30 seconds with that. Can we see in easy choices for S, V, and W such that U ends up non-negative? Well, there are easy choices, of course. We can vanish S, we can vanish V, we can just, take W large enough to cancel this 6,540 value. No, actually the other way around. We need the negative one to cancel this negative. So we vanish S, vanish, say, W, and we take V large enough to, overweight the effect of this negative. And that will give you the positive value for U. That will be one option, for instance.